Is this recorded?
You're live on the internet.
Live on the internet. Oh, wow, great.
So NJAA office Wi-Fi?
So more than you people have to see my bad communication skills. All right, everybody. Why don't we start the we'll start the meeting. Should we lower the lights? Wouldn't be a good idea. All right.
Because all I can see is black screen. That's it. I want to see the people. So.
Oh, I hear you. Okay. Okay. All right, everybody. Well, first off, the first thing I'll say is, for tonight, there's cookies back there. There's sodas. So please help yourself. Unfortunately, they're not the good stuff, aka the Girl Scout cookies, but you know, we'll see what we can do. Maybe next meeting. And another thing I'd like to mention is everybody say a say a prayer for Steve Gale. He's having major heart surgery, I believe, this week. For those who have heard, I think like 6 arteries clogged or something like that. Didn't sound good.
Next week,
Yeah.
or he had this week?
Monday, I guess. Yeah. So, do you know any of the details,
They
Wayne?
were going to do it today, but they had given him a blood thinner when they did the cardiac catheterization to put the dye in to image, where the blockages were, and it has not. There's still too much of it there, so they have to wait until it's out of his system. So they're going to wait until Monday.
How many stents does he haven't put in?
Well, he has 6 blockages, and he has damaged heart muscle. But whether it's stents or what, exactly what they're going to do, I don't know. There's several things. They could do bypasses, they could do stents, they can do this balloon angioplasty thing. I don't know what they're doing, but they're fixing it.
Personal information.
Yeah, let's not discuss this. But anyway, I hope, just to let everybody know, we hope Steve gets better. And I'm really sad about that because Steve's a great person, and also he's always been a valuable contributor to the group. And speaking of contributions, we recently did some imaging and drawing of Mars over the past month. And this encompassed using the RCX 400 coupled with the new camera that we have, the DMK 21AU, and something, and the filter wheel. And on the 26th, we were lucky enough that Vlad and I were here to do it together, and that kind of made it easier because Vlad was up on the platform changing the filter wheel and jiggling the camera when need be. Meanwhile, I was down below working the computer to take the different images and set the exposure. So what you're looking at right now is you're looking at a picture of Mars taken on the 26th, and I think this was probably taken around 11 o'clock p.m. here. So it's the 26th, but that's the Eastern Standard Time, not UT time. And so you can Vlad did a pretty amazing job on the processing too. You can really see some fine structural detail there. And it's just incredible. If you see, there's like the little portions here that are kind of like they kind of look like dot-like features that come out from this section, which you could see if you look at topography maps of Mars. It's just the amount of detail that he was able to get out was really good. And I think you should be able to see it on the iPad too, which is dead. So I'll pass that around if you guys, because then you'll really get to see, how good the image is. And again, that was all processed by Vlad. My images did not fare so well. Now, okay, well, here we go. So this is my image. And this is the last image we took, which was around midnight. And it doesn't have the detail. The detail's not as good as Vlad's. I think maybe I overprocessed. I don't know. I'll have to give another try at it. And But what Vlad and I did that night, which was helpful, was we refocused for each exposure. Although I don't know, I'm not sure, because the one set that you had, Vlad, I believe we'd only refocused one. So I'm not sure how much of a benefit we got from that.
The last blue channel.
Yeah.
That was my.
On the second set.
That's on.
This is the last one, but again, I don't know if this.
It was the one you showed me.
Yeah.
Yeah.
That was the one.
I did not use the third set, which is
That's.
all of them refocused. I did not use.
Yeah. This is all of them refocused, and it's this one.
Is slightly later.
Yeah, but your image from before, this is the one we didn't focus on each one. I think we just refocused one. We did refocus the green. Yeah, we refocused the blue, but this one looks better than mine where we focused each one. Now, I don't know if that's just my processing was not done. Maybe it could have been a scene. It was lower than 2. I mean, it's when you're doing planetary imaging, it's always a mystery sometimes what's actually occurring. But the one thing that Vlad and I will definitely comment on was that the scene that night was excellent. There's no doubt about that. It was a really good scene. And even the temperatural difference with the scope between the RCX will tell you, thank you, Bill. The RCX will tell you what the temperature difference is between the ambient and the internal optical tube. It wasn't much. It was like, what, 5 degrees? Yeah. Wasn't very much. Whereas what in the winter it used to be what, like 20 degrees, 30 degrees?
Yeah, like in the spring and the fall sometimes it gets up to 20, 25 degrees.
Yeah.
So you get a lot of...
And at the same time, the whole tube is made out of carbon fiber. Now, people will tell you carbon fiber is great because, oh, it doesn't flex in between your exposures, yada, yada. Same time, I've talked to some people high up, you know, I guess in the... how would I say high up? Well, some of the manufacturers, I've talked to them about it. And, you know, yeah, you don't have to change your exposure much with a carbon fiber tube. No, it won't expand and contract, but at the same time, it won't let the heat out either. Aluminum lets the heat out. So we kind of got lucky in that the tube was ready to go that night. We didn't have to worry about turbulence inside the image. Now, as I was saying, Steve, at the same time, was taking images. He was drawing images, and that actually, yeah, that came out pretty good. Looks better than it does on my screen. Although the big difference is Steve correctly, he put down the time in universal time, whereas we had it in, before I mentioned, I was just going by Eastern Standard Time, but it's basically the same thing. And Steve did this drawing before, a few hours before we did our images. So he did this about 9 o'clock, and we started our images around 11 o'clock due to technical difficulties, aka frustration. And I think, did we have clouds come through, or we were just fooling around with the camera? Yeah, we had to wait for the clouds to move out. Now here's a comparison, and kind of what you're seeing, I believe, is that this is Sirius Major here, and Sirius Major is here. Yeah, but the interesting is you kind of have these spiking structures that are on the side of it, which Steve is definitely capturing, too. So the gist of it is, but remember, the planet is rotated, and there's about a 2 to 3 hour difference between our image and Steve's drawing, and also at the same time, Steve rotated to keep the cap down, whereas ours is not rotated. So, but it actually looks pretty good. But where Steve definitely beats us is the fact that, you know, we do a lot of work to get one good image, and it's very time consuming. Whereas Steve, you know, the master drawing, he's getting about an image a night. You know, every clear night he's getting an image. So here is his image on May 31st. And now another interesting thing about if you go out almost every night and look at Mars, roughly about the same time, you'll usually see about the same surface features because the Mars rotation rate is what is it? Wayne, could you
Well, it's real close to a day.
Yeah, it's close to a day. It's close to a day. So you will tend to see the same surface features each day. Now, I show this one because this is the Steve Gale's 531 image, which that's in universal time, which is about the same as when, Vlad took this image. But it's hard to see a correlation. And I think actually in this image, the cap is up. So it doesn't really show as well how similar they are. But here's two images that Vlad. Is that when I was with you? We took these images or that was a separate night that I wasn't here. That was a separate night that I wasn't here, right? So we have a third set that we haven't even looked at yet. On top of the Saturn images. Yeah, but we'll do that more in the next meeting because I don't want us to run out of time tonight. But we have more images that we can look at. But again, Steve was able to capture another image drawing on June 1st. And the interesting thing is that, I'm not doing good on my Mars features, but you have this feature coming down here, going across, coming down here. And then I think at the next night, he kind of captures, you see, it's the next night. And again, like I was saying, you're seeing the same features, okay? So here's the night before. And then here's the next night around the same time, and you're getting the same features. Now, Steve noticed it doesn't show so well. I don't think it shows well in these drawings. No, on the screen due to the brightness. But he noticed that you have the polar cap here, but then he was getting a bright area here, which was a cloud type feature, which I'm pretty certain, I have to double check, but I think this is the Hellas Basin, and the Hellas Basin tends to get clouds over it, which is quite interesting. There's certain features on Mars that tend to always attract clouds, like the volcanoes tend to always attract clouds. Just as on Earth, we tend to get clouds over the same mountain ranges and different features. Yeah, like here, I don't know if you could see it. It's like he tried to some way project that this area is bright, but this is where there was like a big bright cloud over that feature right here, which I believe that's the Hellas Basin, which is known to get clouds in it. This was done using his 12.5-inch Dobsonian. And he's getting really nice detail. Like, you know how we got that, we have like that whole, we have the polar cap, but then you have the hood kind of going over the polar cap, and you could see he's definitely seeing that here. And then here's another image again showing that cloud type feature. And this is on that was June 8th and June 9th, yes. And that's the end. So don't leave, anybody, because we'll have our next candidate up. Let me switch computers real quick. Does anybody have any questions or technical? Another thing I'd like to discuss at next month's meeting. Wow. Didn't see that coming. It's like, where were you on the 9th? I don't know. Liar! At the next meeting, I'd like to discuss, I'm going to go over a little more, well, the actual topic for the night, I'm not sure yet. But I'll probably go a little more over some of the planetary images that we've taken. But I've also like to discuss getting a new camera. There's a new camera out that's reasonably priced around $300. And it's nice because it has a large sensor, but you can also use just a small portion of the chip too. But the beauty of getting that camera is that we could start to do large areas of the moon, but we'll be able to get, because the sensor is large, we can capture, say, a good size portion with that sensor. Or, for example, sunspots, we can get the nice area around the sunspot or a sunspot grouping. Whereas I've tried to do that with the DMK, but it tended to be that you had to do a mosaic because the DMK just doesn't have a lot of pixels. Whereas with this sensor, I think we'll get a lot of pixels at one time, and you could even make a nice print of it because you're capturing so much information.
Hey, Bill, a quick question. When you did the images on the RCX, did you turn the fan on before you started imaging?
Yes.
How long?
Not too long. I think.
It takes 5 to 25 minutes for that to cool down with the fan before you start imaging.
Yeah, I mean, it was probably, how long do you think?
Yeah,
Maybe 20 minutes?
when we're about to start, it was cloud, so probably, and by the time we set up the computer and focus and all, it was kept running, so probably around that, maybe even more.
You want to leave it off during your imaging because it does introduce vibrations.
Yeah.
It's only for ambient cooling.
Actually, I don't know about that because I didn't notice. I think we did a test one time and we didn't really notice a big difference.
That's what the manual recommends.
But I don't think they're correct because we did some testing on that and I don't think we actually noticed a big. We actually noticed. Actually, I remember when the temperature is low and there's not a big differential, it might be beneficial to shut off the fan. But I'm sure when I did some testing last year, when there was a big differential in temperature, turning off the fan was actually very detrimental. You could notice how the image went bad when we shut it off. But I think that's because you had a big difference in temperature, so you needed, even with the vibration, you needed that air moving.
Okay, thank you. He's Mike. Nobody can hear you.
That's good. Well, I've just.
No, thank you. Thank you.
Well, our speaker tonight, as you know, is Mitch Revalski, and I am more than pleased that Mitch is here to talk tonight. Seeing how he's now a Ph.D. candidate in astronomy for Georgia State, and so I'm pleased to present Mitch. If nobody can hear me.
All right.
Probably good.
I'd like to thank Bill for inviting me to talk tonight. As he mentioned, I am a beginning PhD student. I'll be starting in the fall at Georgia State University. I just finished up my undergraduate work in physics at the College of New Jersey. And next year I'll be starting down at Georgia State, pursuing a master's in physics and then a PhD in astronomy. So my goal tonight is twofold. Mostly what I want to do is give anyone who's unfamiliar an introduction to gravitational wave astronomy. It's a topic that often is made more complicated than it has to be, and I firmly believe that everybody can understand it at a really significant, strong foundational level if you just discuss things conceptually, if you don't try and go too deep into the math. And then because this is a research meeting, I'll talk a little bit about some of the research that I've done in gravitational waves during my 4 years as an undergraduate. So just a rough outline of what we're going to go through. First, what are gravitational waves? I'm firmly against using acronyms and PowerPoints, but this is the one time I'll use it because it's in there about 1,000 times. How are they generated? What sources produce them? What are we doing in order to try and detect gravitational waves? And what kind of astronomy can we do with them? What can we learn from gravitational waves? Then we'll briefly touch on where the field stands today, where the field is going in the future, and then again talk a little bit about my research in gravitational waves. So throughout the presentation, I want you guys to feel free to ask questions as I kind of hit the end of a slide. Feel free to ask me a question. You don't have to save them all to the end. I know I'm the type that if I have a question, it's eating my mind away and I'll lose attention. So please feel free at the end of a slide to just raise your hand and we'll deal with any questions as we go along. So first off, kind of just a working definition of what gravitational waves are. Everyone has their own definition. There's a million different ways to put it. This is the way I'm going to put it. Gravitational waves are ripples in space which travel at the speed of light and carry energy away from a system, conveying the system's changing gravitational field to its surrounding objects. So that's a mouthful. Don't worry about it right now. Just keep it in the back of your mind. So before we even talk about waves, before we talk about gravitational waves, I just want to talk a little bit about gravity and what we mean by curved space and space-time and all those sorts of things. So when we have space that doesn't really have any matter in it, we usually describe it as flat. It's flat space-time. And all that really means is if you put an object anywhere here, it will basically stay right where it's at. It's not going to go zipping off in some direction. It's basically going to stay there. Now, when you have some massive object, like a star, a planet, a black hole, whatever it is, we can now describe it as curving the space around it. And what that means is, if we place something nearby, it will feel an attraction. They will be gravitationally attracted to each other. Unless something's holding them back, they should accelerate towards each other, and they should eventually collide or do all sorts of fun things. So that's what we mean when we say curved space-time. Basically, all we're saying is it's a type of potential. You can think of this as the very simple model. If you're standing at the top of a hill and you kick a ball, the ball is going to always try and roll downhill. If it rolls uphill, call somebody. That's really interesting. So the point is, down here in this well could be a black hole, a star, anything like that. The point is, the more massive the object is, we can describe it as having a deeper well or a stronger well, anything like that. It's just a mental image for us to be able to describe gravity, to describe potentials and all these things. All we're saying is, the more massive things are, the more rapidly things will try and fall in towards them, the more curved space-time is. So that's just an image to keep in the back of your mind.
When you say curved space-time, are you saying that obviously a black hole will warp the space-time around it? But say the planet Earth, does that have a potential well, and is it actually changing?
Sure. So the question is, do things like the Earth, things that are less massive than black holes, do they curve space? Yes, they most certainly do, but they do it to a much less significant degree. So things like black holes and massive stars, they move away. It takes time for that object to realize that that curvature has changed, and that's basically just going to be governed by the speed of light. So however far away it is, that message is going to travel at the speed of light. Any questions on that before we move on?
So that's kind of showing the wave going out from the object.
Exactly. So there's lots of analogies you can use for this. You know, if you're in a pond and you throw something, you see waves move away from it. Very similar idea here, except instead of a rock falling through the water, this is a planet bouncing basically in its own gravity, if you will. Another question over there?
Yeah. Was it surprising that gravity moves at the speed of light? Because if you're like electromagnetic radiation, that is, well, like the formula for the speed of light. It's like it's 1 over the square root of the, you know that formula. So
Yep.
but those like electrical properties of a vacuum.
Sure.
And that these electrical properties of the vacuum, if I'm taking some license here, they're also regulating the propagation of a gravity wave. Does that surprise anybody?
I'm not sure what the surprise was initially. So the question is, electromagnetic waves like light travel at the speed of light, and mathematically there's constants that we can measure, like the permeability and permittivity of free space. And when you go ahead and work out mathematically what the speed of light should be, you get that it's a function of those constants. But gravity, that's an excellent question. I don't know if there's that same surprise. So when electromagnetism was coming about, that was a surprise, and we say, hey, we, through these empirical constants, get the same result that we measure. I'm not actually sure. I have to think about that when I get back to you. Good question, though. So, shifting gears a little bit, now we want to talk about what sources produce these gravitational waves. So, in general, as you saw with the ball rolling around that mesh, basically any motion can change the curvature of a space-time. There's specific cases where it won't really do anything, but in general, whenever we're going to be moving mass, then we're going to be creating gravitational waves. So some examples where we see this in astronomy, cases which are significant enough for us to want to measure and might be large enough effect for us to measure, are binary mergers. So kind of in this picture here, two stars spiraling around each other. Core collapse of massive stars. So when massive stars collapse, they can have very turbulent cores, and there's an immense amount of energy released, and a significant portion of that can be in gravitational waves. Along with a couple other cases, including Big Bang inflation. So there's been a lot of talk in the news lately about some indirect evidence for gravitational waves. I'll go into that a little bit later. But that's kind of a big question in a lot of people's mind, because it tells us a lot about our model of the universe. Question before we go on.
Did you just say that when a gravitational wave occurs, that could kind of be a portion of the energy that comes out of a supernova?
Yes.
So it's kind of like with the whole thing regarding a neutrino, how they found out, oh, this is the missing stuff. So then that kind of made sense. Are they kind of trying to do that with gravitational waves also, saying there's some amount of energy that's not accounted for Or like, you kind of get what I'm trying to ask?
Sure. So the question is, some of this energy in, say, a collapse or things like that is being released in gravitational waves, and was that unaccounted for previously? And that's exactly what we're getting to right here. So in a binary merger, we have two stars that are orbiting around each other, and this was kind of the first very substantial key to proving gravitational waves exist. Now, it's still technically indirect evidence, but it's extremely strong. So what we have here are two neutron stars orbiting each other. So we have the dense stellar remnant of a dead star. It's extremely massive, say 2 to 3 times the mass of the sun, but it's crammed down into something about 20 kilometers across. So we have a lot of mass in a very small region. So we have a lot of curvature in our space-time. And we have two of these orbiting each other. Now, one of these, in this case, this is known as the Taylor-Holtz binary. It's just the one that happened to be found. One of them is what's called a pulsar. And what that means is it has very strong magnetic field lines, and so we get radiation being beamed off in either direction, in this case radio waves. So what that means is, as the star rotates, if that beam of radiation happens to sweep by us, we can measure it. We see a big spike in the radio waves. Now, neutron stars, being so massive and so dense, have a very, very high angular momentum, meaning it takes a lot to slow them down. So these are some of the most precise clocks we have. Every time we see that radiation beam sweep by us, it comes in exactly the same interval every time for hundreds, even thousands of years without really any perceptible change down to the nanosecond scale. So what we have here is two stars orbiting each other, and a prediction of general relativity is that slowly these two stars should start to spiral in towards each other because they'd be emitting energy in the form of gravitational waves. Now, previously, there wasn't really a way to measure this. So now we have a very precise clock sending us signals at very regular intervals. So what we do is, as they orbit each other, the star is going to be slightly further away on one part of its orbit and then slightly closer during another part of its orbit, and we can measure how long it takes to complete that cycle. And what we see is, over the course of years, the amount of time it takes to complete that cycle is slowly shrinking, which we interpret as a shrinking of the orbit, meaning the stars are getting closer and closer together. So this is one of the few graphs I'll show, and this line here basically is the prediction of general relativity as to how quickly that period should be shrinking, and then the little black dots on there are the data. So as you can see, there's almost an exact fit. It's to within 1/2 of 1%. So there's a lot crammed into just this one slide. Are there any questions on that? Okay.
Which star is that?
Sure. So this is the Taylor-Holtz binary. So they're both two neutron stars, one being a pulsar. They still have about 300 million years till they merge, believe it or not. They orbit each other within about 4 solar radii at their furthest point and about 1 solar radii at their innermost point. And their orbit is shrinking by about 3.5 meters a year. So we're able to detect that.
How long does it take them to orbit each other?
It takes them, don't quote me on the number, roughly a third of a day. Roughly, yeah, right at 7.75 hours. Any other questions?
Yeah, doesn't the orbit of the pulsar, sorry, not the orbit, the rotation pulsar, that's not affected in any way on how it, on how the orbit decays to the other, to its binary partner? The thing is, as the moon moves further away, the Earth's rotation slows, right? I thought there'd be some sort of interaction.
Sure. So the question is the rotation of the pulsar affected at all by basically the partner, by the binary partner? I think, I can't say for sure that the answer is no, because I'm sure at some order it is. But again, these stars are rotating very, very rapidly. This particular one rotates about every 17 seconds, and you have a couple solar masses within a few kilometers rotating very quickly. And the separation between these is on the other order of a couple solar radii. So unless these stars were already elongated or something like that, in the case of the Earth, we have a bulge. There's not a whole lot to tug on to slow it down, so to speak. So if it's basically a perfect sphere, there's not much you can do to tug on it. If it gets out of that kind of spherical shape, then absolutely, then you can really start to slow things down.
It's just because, well, all the mass is so concentrated in a perfect sphere that, okay. Thank you.
I think what he's referring to is the friction of the tides on the Earth, which is slowing the Earth down, which is transferring the energy back to the moon.
Sure. So that Right. In regards to the tides on the Earth and that correlation, there's two parts to that. One, the Earth is not a perfect sphere, and the other being that the Earth has oceans, and the oceans can move, and those are able to be pliable, so to speak. These neutron stars, unless you get them really, really close to each other, their gravity is so strong, their self-gravity is so strong, their binding energy is so high that you really can't pull them out of a spherical shape until they get really, really close to one another. In which case, then they'll start to do that. All right. So the next emitter that we'll talk about briefly are supernovae. Not all supernovae are believed to be gravitational wave emitters, but it's believed that they could be. So this is an area of very active research, looking at what happens in the core of massive stars when they die. So there's some models that say it's very kind of controlled, they just bounce right out and there's no gravitational waves. There's other models that say it's very turbulent, you have lots of mass moving and accelerating and emitting a large amount of gravitational waves. So there's all sorts of work that goes into that, but because these are such energetic events releasing so much energy, it's believed that you could have something on the order of 1% of the binding energy released in gravitational waves. So we'll go through some numbers a little bit later to kind of compare that, but you're talking about orders of magnitude more than the output of the sun released in a couple of seconds in gravitational waves. So it would be a very high energy, very short duration burst of gravitational waves, which is kind of an easier signal to pull out sometimes because it's this huge spike that would show up in your detector, which we'll talk a little bit about later. Going kind of into what some of your questions were, one of the additional ones is the bump on a star model. So again, we just spent this time talking about how neutron stars are very spherical, but it is still possible for them to have slight deviations from spherical. Their crust is so incredibly strong that you can have very small what they call mountains. And we say mountains, we're talking millimeters or less, but in that amount of volume, because these are so dense, you can have something on the order of the mass of the Earth in there. And because this can be spinning dozens, sometimes hundreds of times per second, that's enough to perturb the space-time around it and release gravitational waves. Now this is believed to be kind of one of the weaker emitters, and some recent work that I've seen has basically said these bumps would be so small just because the neutron star is self-gravitating so much that we may not be able to detect them, but that one's still up in the air. So I just thought I'd put it in there as another source.
In the neutron star, what's the difference in density in the core versus, let's say, at about 20 kilometers? Right?
Sure.
Radius, like at the surface.
So the question is, what is the difference in density between the core and the surface of a neutron star? Again, don't quote me on the number. I believe it's roughly 2 orders of magnitude, so you're talking a factor of 100 roughly. But when you talk about what the actual density is, again, there's lots of fun quotes. It's like a teaspoon of neutron star would be 200 million tons, some insanely large number that we just really can't fathom. So it is slightly more dense at the center for sure. But because the neutron star is basically just a bunch of neutrons pushing against each other, the electrons have been crammed inside the nuclei, there's just no more room. So the density spread is not necessarily as large as you'd think. But that's an excellent question.
What would cause a mountain or so?
Sure, so what would cause a mountain on a neutron star? The idea behind that is that neutron stars actually have kind of a crust, if you will, above the neutron layer. Now that's a big question mark as to what exactly that's made of and all that. But basically, as the star tries to change shape ever so slightly, there will be a resistance to that. The crust will resist that, and you can actually get slight cracks in the crust. And the way we know this is we look at these pulsars or neutron stars sending these signals, and you see sometimes a glitch where the period of rotation changes ever so slightly, but very quickly. And that's basically believed to be when they have what's called star quakes, and the star can actually kind of crack that crust a little bit and change that distribution of angular momentum and change its period a little bit. Good. All right. So the last bit that I'll talk about is Big Bang. So during the early universe, we have a lot of mass, very dense states accelerating very quickly. Kind of the overall very, very toy model picture is that we have some sort of quantum fluctuations, everything is not perfectly symmetric, and that's going to cause very powerful gravitational waves to be made. Again, very theoretical. And now we have a kind of possible indirect detection. So in the news in the last 2 months or so, there's been a big hubbub over BICEP2. Basically what they are doing is they are looking at the cosmic microwave background. They're looking at the radiation that's left over from the formation of the universe. And what theory predicts is if gravitational waves were produced during this time, then they should induce what's known as a B-mode polarization, kind of this twisting polarization of the light. It's just the way that the light happens to interact with the gravitational waves. And when they went ahead and did this very subtle measurement, they found exactly that. That's recently come under a little more scrutiny and attack because there's a couple other things between the cosmic microwave background and us that can produce that similar type of polarization. And some people believe that they may not have fully accounted for all of those things yet. So it's very controversial, but there's a couple other projects coming up over about the next 1.5 to 2 years that should be able to kind of substantiate that or disprove it pretty easily. One of the big ones being Planck. So this is kind of the model of the sensitivity you need, and BICEP2 is right on the edge, and then the Planck satellite, which should be our next big step forward, should answer that question rather quickly. Questions on that? All right, so now we'll switch gears again and we'll look at detection. So the question is, how do we detect gravitational waves? Real quick, before we look in that, we need to discuss what exactly we're trying to detect. So as we said, we're looking at curves in space-time, which is very different than detecting light. So we are very good at detecting light, at detecting photons, which have their wavelengths determined by these small atomic transitions, electrons dropping down, giving off photons. But in this case, the wavelengths of the gravitational waves are determined by the bulk movement of the source. So if you have two stars moving around each other, the wavelength of that wave is roughly the size of that system. So they can be huge. So the wavelengths could be kilometers larger. It's even theoretically possible to have ones that are the size of the universe, which would be very difficult to measure. You can also have smaller ones in a number of situations, but it's just important to kind of think about these types of differences. Now, where this comes in handy is that it gives us different information about what we're looking at. So light can carry all sorts of information. It can carry information about temperature, about the amount of energy being released, just about anything that you can do with spectroscopy. Whereas this is carrying information about the total mass of the system, its distribution, how it's accelerating, how it's changing over time. Again, an advantage of gravitational waves is that while light is easily blocked by dust and by gas in between us and the source, gravitational waves travel through nearly unperturbed. So basically the idea is gravitational waves are just these ripples in space. They move things, as you saw before, they oscillate the space, and things in that space will oscillate, but they basically just plow right on through without really interacting a whole lot. And I'll talk about that a little bit more later because that's been kind of the aim of my research, is figuring out exactly how true that is. The last thing to mention is that electricity and magnetism is a very strong force, much stronger than gravity, and this kind of is counterintuitive. So if you've ever played with two magnets, you can get super strong little magnets and you can stick them together and then almost not even pull them apart, and they're very small. But when I stand here and lift this bottle of water, I have just overcome the gravity of the entire Earth. So the entire Earth I have just beaten by picking up this bottle of water. So the reason that gravity dominates on these large scale is there's only kind of one sign, if you will. Charges, we have positive and negative, and basically in the whole universe, they tend to basically cancel out. Whereas gravity builds up. You keep adding more mass, you get a stronger gravitational pull. There's no nirvana. It just gets bigger and bigger and bigger. So because of that, these gravitational waves tend to be really weak. So we need to get pretty creative with our detection methods. So there's three main types of detectors. The first is known as a resonant bar detector, or a Weber detector. The second one is laser interferometers, and the third is pulsar timing arrays. And I'll go through each of these briefly in some detail. So a Weber bar, named after its inventor, is literally a giant bar of metal. And it can also be a spherical shape. There's a couple different configurations that work. But essentially, what you do is try and match the size of your bar to the frequency of the gravitational wave you're trying to detect. And if a gravitational wave of that particular frequency comes in, it will be amplified within the bar, and you will be able to measure that. The catch is, it is only able to detect pretty weak gravitational waves. And I'll go into a little bit more detail what that number means in a little bit. So back in the 60s and 70s, there was kind of a little bit of excitement. It seemed like these were working and that they were making detections, but then it could never be confirmed. So there's still a few of these operating, but unless we get a very strong gravitational wave, such as from a supernovae event or two very massive black holes merging, it's probably not going to be able to see everything that we want. The second one, and this is kind of where most of the money is the main focus, this is where a lot of people are working right now, is laser interferometers. So what we have here is a relatively simple system. So we have a light source, a laser, that sends light out to a beam splitter, which splits that light in half. And then each half of that light goes down one particular direction, perpendicular to the other, to a set of mirrors. Now, if these two arms are exactly the same length, that light will split, travel, and bounce off each mirror, and then come back at the exact same time as the other beam. So the two beams will come back together at the same time, and you can make them interfere and either cancel out the light or constructively add. There's all sorts of different things you can do, but basically you can tell that those two path lengths are exactly the same. Now the idea is when a gravitational wave comes in, it will alter these lengths. As you saw, the gravitational wave stretches in one direction and shrinks in the other. So when that happens, one path will be slightly longer and the other path will be slightly shorter, and the light will come back at two different times, and that interference pattern will change, and it will change based on the wavelength and the frequency of your gravitational wave. So to give you an idea of the sensitivity that's necessary here, the main operational one right now is called LIGO, Laser Interferometer Gravitational Wave Observatory. And that has arms here, they call them arms, which are about 4 kilometers long. And within that 4 kilometers, they're looking for changes in the distance about the radius of a proton. So you're talking extremely, extremely small changes. So 10 to the minus 21. So 1 part in 10 to the 21 is what they are trying to detect. Insanely small, requires a lot of advanced suspension, a lot of cooling, a lot of very precise lasers. There's a lot of things that you have to do to beat down the noise in order to be able to even possibly detect this. So this one has been offline for a little while, and they've been upgrading it to what they call advanced LIGO. They've installed more powerful lasers. They've improved their suspension systems, a number of things. That'll be coming back online either this year or next year. And they believe it should be able to make significant detections within the next 2 to 3 years. Never quote numbers on detecting gravitational waves because they've always been surpassed from one to the next. Any questions on that before we move on?
Yeah, is there a certain length that those beams have to be, or how does that play a role?
Sure, so the question is there a certain length that these arms have to be? Overall, you want the arms to be roughly the length of the wavelength you're trying to detect. So each type of detector, based on the length of this arm, will have a different sensitivity. So detectors with very small arms will be sensitive to a certain frequency, and detectors with very long arms will be sensitive to a different frequency. There's still kind of a band there, so if you look at the sensitivity, there's kind of a range of sensitivities with a peak sensitivity. And LIGO is built, again, don't quote me, there's a number of resources you can find online that show what types of sources it hopes to find, usually coalescing sources of a certain medium mass, of a certain medium distance, kind of, try and get the widest shot possible in order to detect as many events as possible. Other questions? Great, excellent questions all around. So the last one that I'll talk about is called PTA, the Pulsar Timing Array. And what this does is make use of pulsars in a slightly different way. So we have the Earth here, and we know lots of pulsars all around the galaxy. And what we can do is, again, these are sending those very regular signals, so we're receiving pulse, 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 pulse. We're getting these very, very precise signals. And if a gravitational wave passes through, it should change the length of that pulse because it will stretch or shrink the space between us, and then as it passes through, it will do the same thing on the other side. So the idea is if you can correlate a change in that arrival time between a variety of pulsars and see that it's different from one side to the other, then you can get an idea that a gravitational wave has passed. You get an idea that it has either shrank or stretched that space and saw that amount of time it took for the signal to reach you has changed. So there's a number of pulsars being monitored, and there's a number of different groups doing it, but they're all kind of under one big organization, which is the International Pulsar Timing Array group. So there's always the, why is this important? Why do we care about gravitational waves? And the reason is because it allows us to do a lot of things that we can't do in astronomy right now. So for example, it will let us hopefully look into the earliest portions of the universe. So we can only look so far back before light just hasn't reached us, before we hit what we call the last scattering surface or the dark ages, whatever you want to term it. But basically there's a point where light just couldn't propagate and the universe was too dense and it couldn't reach us. But theory says that gravitational waves should be able to pass right through all this and give us pictures all the way down to very, 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 very close to the Big Bang, much closer than we can get with light, much closer than a second. In addition to that, it gives us an entirely type of different information about mergers. So for example, black hole mergers, and here's just a picture of a simulation out of University of Oregon. They kind of describe what it gives us in terms of a sound. It lets us see what is going on at the very close interactions, because again, black holes are black, they're not emitting a lot of light. If there's gas and material around them, then we can see that, but this is giving us an entirely different type of information about the space-time around them and letting us probe those mergers in regions where we just can't really do it otherwise. Again, going back a little bit, some of the neutron star structure, it can let us see if there's bumps, if there's not on the surface. Supernovae processes, it can let us see if these cores of core collapse supernovae happen to be turbulent or if they don't appear to be turbulent, or what exactly is going on in the core. That's still, again, very much in development. And then the big one is test general relativity. Everyone is always trying to break general relativity. As far as we know, general relativity has passed every test that we can put it through. So Newton's laws worked very well for a long time, and then when we got to the bigger scale, we needed something a little more complex, and general relativity came in. It's made a number of, people have made a number of predictions using general relativity, such as the advance of the perihelion of Mercury, the amount of time it takes Mercury to go around, bending of light, gravitational waves, all those sorts of things. And general relativity has proven, yes, the measurements match the theory, but gravitational waves are the last not directly detected prediction of general relativity. So that will be a really exciting thing. And then again, of course, much more, because once we actually detect gravitational waves, assuming we do, which we very strongly believe we will, then it will allow us to do things that we may have not even thought of yet. So I always leave question marks. So right now, the field is hopefully on the verge of the first direct detection in the next couple of years. There are presentations just like this 10 years ago that would have that same number up there, and hopefully there won't be ones in 10 years from now that have that same number up there. So we've been creeping closer and closer. We've been getting more and more sensitive instruments, and it seems like we should be getting very close to the sensitivity we need to relatively easily make detections. So these what they call second generation detectors are coming online, the advanced LIGO, things like that. That should allow us to make these detections, and they've begun planning on what they call third generation detectors, which should allow us to detect mergers and things like that at much further distances. It should allow us to detect much weaker sources like rotating neutron stars and things like that, and allow us to get a lot of signal to be able to do a lot of astronomy and physics and astrophysics with what we're getting. So one of the biggest ones that's being pushed right now is known as ET, the Einstein telescope. This is similar to LIGO in a number of ways, but also different. So it would consist of a triangular configuration with a variety of different interferometers in between. So it has lots of mirrors and lots of light being bounced around. And what it actually has is set up to detect different frequency gravitational waves. So it has much longer arms. They're about 10 kilometers. And it has high frequency and low frequency detectors in order to be able to do a lot more physics with that. Again, this is all still on paper. It hasn't really been moved forward yet. When I was at a conference recently, one person pointed out very well that as soon as gravitational waves are detected by LIGO, that will probably be the moment that funding starts very significantly. But it would allow us to do a lot more with gravitational waves than we can currently. And then just kind of at the bottom here, one that people dream about is known as BBO, the Big Bang Observatory. This is kind of a similar type of deal, but you would have it in space. So LISA is a design which you have these types of interferometers basically in space because you don't have to deal with the seismic noise of the Earth, and trucks driving by, all that sort of stuff. And the Big Bang Observatory is an idea to expand that, so you would have basically 3 separate interferometers at various positions along the Earth's orbit, and it would allow you to do extremely good gravitational wave astronomy, but again, just on paper so far.
When we started to detect the gravitational waves, now, how well are we going to be able to determine what created them and from where?
Excellent question. So the question is, if and hopefully when we detect gravitational waves, will we be able to disentangle where they're coming from and what is producing them? So interferometers like this are actually not terribly good at localizing sources. They can be in a variety of directions and you'll still get the signal. But what they can do is help you disentangle what created them. So the frequency of the wave and the wavelength are going to be intrinsic to what produced them. And that's where a lot of work is going into right now, is trying to simulate that. So in a computer, we merge black holes, we crash galaxies into each other, and we see what type of gravitational waves get produced, what are their frequencies, how strong are they. So there's a lot of work right now going into trying to see what the gravitational waveform will look like, so that way when we hopefully see them, we'll be able to say, okay, that came from this type of source, or there's a very high probability that it came from this type of source, things like that. So that's an excellent question. So, summary of the first part here before I briefly go through some of my research. Again, hopefully now you have some sort of picture that gravitational waves basically just represent the changing gravitational field around us. As things move around, all the stars, the planets, everything are pulling on us, and as those things move around in space, those pulls are all changing, and those pulls and those changes propagate as gravitational waves. Gravitational waves are interesting for astronomy and astrophysics because they yield a very different type of information than what we can normally get from light, and should allow us to probe a lot of different things that we can't currently do. And the last point, a lot of effort is being put into detection right now. We think we're kind of right on the cusp. We should have the technology and the infrastructure and the hardware in place to make those detections, but you just never know until we actually get it. So before I move on and briefly go through a little bit of my research, are there any more questions on that so far?
In the example you showed with pulsars, binary pulsar,
Mhm.
right, that are, you said that the distance between them would be about 1 or 2 solar diameter, right? So about 1, I guess, million kilometers, a couple of million kilometers. Something.
Yeah.
Yeah. So what would be the let's say wavelength of gravitational wave created by that sort of system?
Sure. So the question is, what type of wavelength and frequency do we expect from something like the binary pulsar, which has the period of about 7 hours? So as the stars spiral in, their period will become shorter and shorter, and the frequency of those waves will get higher and higher. So if you want to think of a very simplified picture, as the stars are orbiting, and basically as they come towards you, they are compressing that space, or they're stretching and expanding the space. So every time a star comes around is when you will get the greatest change in that space-time, is when you'll get either a crest or a trough in your wavelength. So basically half of the orbital period is every time a star is going to come around and face you, and that's when you're going to get your greatest change. So that's why it's really difficult to detect these waves right now. See, even for example, that system, which is very close, they still have a period of about 7 hours. So as they get very close and they start to orbit in a couple of minutes to a couple of seconds until they finally collide, that's when the gravitational wave signal is believed will pick up significantly. And that's what we think right now we'll be able to detect, are those final moments. And then as we go and advance our technology, we're hoping that we can see them earlier and earlier and be able to see those gravitational waves building up and getting stronger and stronger.
But for that, you said it's going to happen about 300 million years for that system, right?
That particular system,
So we have a long way.
yeah, so that particular system is a long time. So there is a big hunt for shortest period binaries. So that system has a period of about 7.75 hours. Right now there's a relativistic white dwarf binary known, and that has a period of a few minutes. But even still, those merger times are nowhere on our human life scale. So there is that constantly that hunt to find binaries that are closer and closer.
I guess the wavelength between the peaks would be, if the period, let's say 2 minutes, you take that time times the speed, which is they move at the speed of light pretty much, right? And that will be, I guess, the sort of the distance of the wavelength. Or is that how it sort of measures?
Roughly, yeah.
If
So
they propagate at this speed of light.
Right, so the
We
wave-
have no rotation.
Right, so the changes propagate at the speed of light, and the wavelength is basically going to be determined by about half your orbital period, give or take.
Yeah,
Yeah.
exactly.
Mhm.
Which will be obviously in that case.
On the order of
obviously
hours,
obviously
couple
very-
hours.
Yeah,
Mhm.
at the end of wavelength will be very large.
I'm curious about that first interferometer you showed, where the wavelengths, they were rather the vibration or the movement in the mirrors
Mhm.
was on the order of 10 to the negative 21 meters. What's the frequency of that laser? I mean, a laser wavelength is in nanometers.
Right. So the question is basically, how do you get around the noise in the laser because you're trying to detect changes that are so much smaller than the wavelength of the laser itself? There's a lot of tricks that people do to beat down that noise, some that I am not qualified to explain. I know they do a number of things, including cooling the masses. They cool a number of things to keep that noise down. And then again, having a long baseline. So you have 4 kilometers, so it's 10 to the minus 21 out of 4 kilometers, which is still an exceptionally small number. There was a recent article, I could dig it out, as to basically how they're getting down to that quantum noise limit.
So basically, they're looking for like a really small phase shift between the two light.
Precisely, you're looking for a small phase shift.
Very small.
Very, very small. Very, very small, yes. So, no, it's a good question. One other way that they get around that, as you saw in the diagram, there's actually 2 mirrors, and what they can do is bounce the light multiple times. And when you bounce the light multiple times, you're basically integrating that effect, and you're stretching it out, you're making it larger. So that's another way you can get around that. Excellent question. So now I'll just briefly go through a little bit of my research that I've done in gravitational waves, just to kind of give you a flavor of what I've done. I try and keep things as non-mathy as possible. I know everyone sitting here can certainly handle any math that I could throw at you, probably better than I. But again, I like to stick to the conceptual side of things. I think that's where most of the interesting stuff is. That's where the good questions come out of. So briefly, I've done research in 2 areas within gravitational waves. So the first is looking at the effects of gravitational waves on interstellar gas clouds and seeing if there's a possible link there to star formation. And then the other is looking at how gravitational waves move charged particles and if they accelerate and emit radiation. So this is just a little model I made up of a gas cloud with a gravitational wave coming in on it. And as we've seen before, the gravitational wave can shrink and stretch things. And in doing so, it's changing the density of this gas cloud ever so slightly. Again, it's going to depend on the strength of the wave and a number of things, but what we're looking at is we see the density of this gas cloud changing slowly over time. So the question we want to say is, can gravitational waves trigger star formation this way? So we know that they can move particles around, but are the effects substantial enough on gas clouds to actually make a gas cloud collapse and trigger star formation? So what we look at is the influence on what is called Jeans mass, which all that really is, again, ignore the math, but all that really is looking at how much mass you need of a certain density and a certain temperature and a certain composition within a certain region in order for it to overcome its own self-gravity. So you have forces trying to push it apart slightly, like electrostatic forces or thermal energy, and basically once you get a certain amount of mass in a certain small enough volume, it will just keep contracting under its own gravity and should eventually form a star if there's enough mass. So what we're looking at is gas clouds that are near that limit. We want gas clouds that are basically there, but they just don't quite have enough mass, or they're not quite cool enough, something like that, to contract on their own. Could this gravitational wave trigger them to collapse? So what we look at is what's called a perturbation model. And basically all this equation is saying is, when we go ahead and poke this gas cloud with a gravitational wave, we just change it just a little bit, what happens? And what we see is there's a couple different cases that can occur. So in one case, the amount that you increase the gravity when you're flexing it is so small that we get just what they basically call acoustical waves. They'll just oscillate and then it'll damp out and nothing will happen. In the other case, if the perturbation is large enough, you'll actually get a runaway situation. So you start the oscillation, and then the enhanced self-gravity is enough to actually continue the cloud collapsing on its own. So that's the interesting case that we're concerned about. So the catch is we want to look at how strong of a wave might be impacting these gas clouds. So we said that when they get here on Earth, they're extremely weak, very, very weak. But when you're closer to the source, the gravitational waves are much smaller, or excuse me, much stronger. So what we want to do is say, okay, if I want to change the gene's mass by X amount, I need a gravitational wave of such and such a strength. And now I want to look at sources and say, is this reasonable? Can this even occur in the universe? And are those distances reasonable? And do a number of limits hold in order to do that? So the numbers aren't important here, but the point is we can find strains, we can find gravitational wave amplitudes that are much stronger than those we detect here on the Earth. Instead of 1 part in 10 to the minus 21, we're looking at, say, 1 part in a million or smaller. So we can get stronger waves, but they're still relatively weak, even when you consider very relativistic systems like very high mass black holes close to each other, or stars about to collapse, neutron stars, things like that. So we see that the waves are stronger close to the source, but they're still relatively weak overall. So it's could definitely be the case that we'll get these density fluctuations in cloud regions, but we may have to be so close to the event that other effects would dominate. For example, if we're very close to a supernova, the gravitational waves may be enough to condense a nearby gas cloud, but the supernova itself may completely blow the gas cloud away. So in order to kind of look at the catastrophic events, the ones that might cause gravitational waves that are strong enough to do this, we'd have to look a little bit more at what the scales we expect are for things like black hole mergers and supernova shocks that are moving out, things like that. Any questions on that before I move to the other part of my research?
How long would it take for a star or for a gas cloud to actually collapse? The only thing I could think of that would sort of be similar would be gravitational sweeping, which I know they're completely different.
Sure.
Gravitational sweeping takes forever.
Sure. So the question is, how long would it take this gas cloud to collapse? A gas cloud in and of itself, even when it reaches the gene's mass, takes an exceptionally long time to collapse. I don't want to quote a number because it's going to depend on the side of the gas cloud and whether it fragments and things like that. But you're talking, hundreds of thousands, millions of years, something on that scale, depending on a variety of factors. But yes, it's going to take a very long time. The key point there is we're just looking to trigger it. Can we make it move in that direction and then have it do it on its own?
And to see if it does it on its own, how much of the collapse do you actually have to witness or observe to say, all right, it worked? Or am I just completely misunderstanding?
No. So basically the question is, how would you tell that the gravitational wave had actually collapsed it? Right. So sure. So this bit is theoretical. So what we're looking at is we're saying stars very close to that limit already could possibly be collapsed down. In order to actually observe this, I don't think it would be observable on human timescales, which sounds rather depressing because then what's the point? But the interesting bit is there's always regions of enhanced star formation within a galaxy. Sometimes it's very obvious where it came from, sometimes it's less so obvious. We say there's a lot of stars forming here and we're not exactly sure why. So it's just kind of looking at that and saying, could this be a trigger for star formation, in certain situations? The answer is possibly, but most likely not.
Well, I just wanted to get a good understanding, which was probably because I wasn't paying attention, but the first part of your research was determining what the numbers were to cause the actual star formation.
Right. So the first part was looking at what strength gravitational waves we would need in order to
what those numbers were. How?
Were realistic. So there's a number of formulas for what the strength of the gravitational wave will be based on the source. So for merging black hole, basically merging binary systems, for supernovae, there's a lot of rough order of magnitude formulas that'll say you should get this strength gravitational wave based on the mass, the radii between the orbits, a number of things like that. So yes, basically that was the point, is we were finding those numbers, finding those strengths, and then saying, are they reasonable? And the truth is, yes, they're possibly reasonable, but they would be so close to the source that we might just blow the gas cloud apart, or it might get sucked in, something like that. Yep, very good. All right, so real quick, summarizing part 2. This was work, I still have the College of New Jersey on here because that's where I did it at, and We just recently presented this work at a conference in Spain, which was excellent. There was a number of very bright people there who were able to have some good discussions with us and point out some things that we could possibly improve. So what we're looking at is, we know gravitational waves will cause particles to move. They'll cause anything that's passing by the wave will move. So the question is, if we have a charged particle, will it absorb energy from the wave and emit radiation? So in classical physics, if you take a charged particle and you accelerate it, it emits radiation, emits light, in order to try and lose that energy, in order to try and get to its lowest potential state. So the question is, if these charges are being moved around by a gravitational wave, are they absorbing any of that energy? What do we really mean by moving around, accelerating? Because as with anything in general relativity, when you talk about moving, accelerating, anything like that, you have to be very careful as to how you define that, because there's always another way to look at it that might be valid. If this is the case, what are the astrophysical implications? What does this mean for cosmology? What does it mean on the small scale? What does it mean on the large scale? And what can we learn about gravitational waves, about the universe, if this effect is occurring? So again, the math looks crazy, but all this is Newton's second law. This is just F equals ma in fancy notation with varying variables. So basically all we're looking at is F equals ma. So in general relativity, you have to analyze the motions of particles in a rather complex way. But if you stick to very, very small regions of space, you can get away with basically a Newtonian approximation. So when you do that, we can say, okay, we can describe the motion in terms of Newtonian forces. It looks like this particle is being driven, is being moved around, is being accelerated, but there's still always the question of, does it feel the acceleration? Is it just the space expanding and contracting around it, or is the particle actually moving, actually experiencing the acceleration? And that's a hot debate, and most people would just say that it's the space expanding and contracting between it. So that would seem to kill the idea right there. But then what we go ahead and do is look at Maxwell's equations, which are our classical electrodynamic equations. Basically, it's telling us whenever you have a moving charge, this is the type of field it produces, this is the type of radiation it produces, anything like that, and also for static charges. And when we go ahead and do that, we look at Einstein's field equation, we get a component from that charge. So again, this looks fancy, but all this is saying is the curvature of the space is equal to the amount of mass energy and the amount of electromagnetic energy that we have in that region. So mass can curve space and charge can curve space. So when we go ahead and look at what type of potential is found by that, again, it looks like fancy notation, but all it is we find a static portion, which is just like a charge sitting there. We say, okay, I can measure this charge here. And we find that there's a time-varying component, which we interpret as radiation. We have a time-varying potential, so we have radiation. So there's equations that we can use, classical equations, to calculate the amount of power that we're going to get from this charge. And it's going to depend on the number of charges, how much it's accelerating, and a number of other angles between us and the charge, things like that. So then the question is, could this radiation be used for detection? Right now we have gravitational wave detectors that are based on measuring changes in distance. This is an entirely different part of the spectrum. It's an entirely different spectrum. This is, again, back to the electromagnetic spectrum. We're really good at detecting electromagnetic radiation. So can we measure this radiation, and would it be able to allow us to use it as kind of a precursor or as a signal that a gravitational wave is passing through a region of charge? And what type of information would this give us about the gravitational waves? Would it tell us about how they move, how they propagate, how they scatter? And again, just a lot of question marks there, because a lot of that's not really known right now. So we need to know the strength of that radiation. The second part, and this is the most important one to me, is this could possibly cause wave attenuation. So the picture is that gravitational waves basically just pass through everything almost completely unperturbed. They can pass through galaxies, everything, and they are basically completely untouched. The mass just moves around, and they barely lose any energy, only a very, 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 very tiny amount of energy. But in this case, if we have charges that are being accelerated and they're emitting light, we have a conversion of energy. So we're taking energy from the wave and basically putting it out in light. And that would mean that the wave is losing energy, and when the wave reaches us, the wave would be weaker than when it was emitted. So this could be really significant in the early universe, where we have lots of free charges moving around before matter started to couple up and all that. and we have very strong gravitational waves. So could this have been a mechanism that would diminish the gravitational waves? So when we start to hopefully get the first detections, questions like this can be answered. Are the gravitational waves as strong as we expect them to be? Do we measure those early universe gravitational waves? And things like the BICEP 2 and the missions that will follow that will be able to help answer some of these questions very quickly. So what our part of the research did was look at a bunch of different types of charge configurations, so rings and spheres like you might find in gas clouds, calculate all the different formulas that will give you what type of power is emitted by them, and then look at the amount of incident energy versus the amount that would be absorbed, and we find that it is 10 to the negative 70th. So I wanted to really come up with an analogy to give you an idea of how small that is, and I just can't do it. So if you divide by 10, 9 times, you get 1 billion. So do it 61 more times, and that's what fraction we're talking about. So it's basically nothing. It's such an extremely small amount of energy that you would probably not notice. But the caveat is, it's still dependent on the frequency of the gravitational wave squared and the total amount of charge. Now, gas clouds can have an immense number of free charges, 10 to the 20th, 10 to the 30th, 10 to the 40th. They can have a huge number of free charges. Each one of those is going to be extracting this little tiny amount of energy from the wave. And then again, the frequency of the wave plays in. So if you have high frequency waves, like very close to merger or supernova events, they're going to be attenuated more, similar to how red light and blue light are attenuated differently when moving through interstellar gas and things like that. It would cause this bias towards what we think we'll see and what we may actually see. So the conclusion we found is that yes, charges should be able to gain kinetic energy from the gravitational waves and radiate. It's still a controversial topic. We had a number of interesting discussions at our conference. People who thought, wow, that could definitely be possible. People who say no, and here's why we think why. So it's still controversial. But overall, we're only taking a tiny little amount of energy from the wave. But since gravitational waves, when they're emitted, have so much power, it could be a significant amount of energy overall. So with that, I will open it up for questions.
So this kind of goes back to what I was asking earlier regarding how a cloud can collapse and how long that would take. What if in a lab, just kind of want to see if this could actually work, what if in a lab you were able to actually see a group of particles accelerate and you saw what wavelength came out of that and you knew a gravitational wave did that? If the same particles are in that gas cloud and you see the same wavelength, could that theoretically mean, like, a gravitational wave did it?
Right. So the question is, could we reproduce this in the lab, basically? Could we produce it in the lab and then correlate that with an astrophysical event?
I think I just found the flaw in that, because the gravitational wave you would see would not be the same wavelength as the one that would come out if, like, the source is right above
Right.
the cloud.
So the problem with trying to replicate that is twofold. One is, yes, trying to match a frequency and wavelength would be problematic. But more than that, making gravitational waves strong enough to actually measure in the lab is nigh to impossible. There's an interesting bit posted somewhere where if you basically put 2 cars on the end of a 20-foot pole and spun them at like 4,000 RPM, the change would be like 1 part in 10 to the 40. So to actually build an apparatus that would make gravitational waves, you can do it. Technically, when I walk around this room, I'm making gravitational waves, but they're going to be so extremely weak that we're just not going to be able to measure them. If you can find a way to amplify them, that would be an interesting bit.
I was thinking of them more just coming through the lab, like just sort of waiting. But even then, they're coming from so far away, they'd have to be the same exact distance, I would guess, from the gas cloud. What are the odds of that?
Okay, so the question is, if you have a gravitational wave coming through the lab, could it accelerate charges and do the same thing? So one's reaching the lab. Most of the ones that we're trying to detect are very low frequency, long wavelength. So the wavelength and the frequency of the radiation that you're going to get is going to be similar. So it's going to be out of our spectrum. So it might be, really stretched out radio waves, something like that. So hypothetically, though, if you could get really high frequency gravitational waves to pass through the lab, could you get charges to radiate?
But that couldn't happen enough where you could actually get good results.
I'm just going to have to say I don't know, yeah, because there's so many other factors when you come to Earth. All of this is done assuming that the charges are basically free. They're not, you know, like around a black hole or something like that. It's really interesting. I'd have to give it some thought. I haven't, and I will have to.
Fantasy.
Yeah, sure. Other questions?
What about our closest system, Earth and Moon? Did anyone actually look into? Does it? I'm sure it's obviously there are some.
Sure,
But
sure.
Is it just too minuscule?
So
to detect?
sure.
Or
So the question is, within the solar system, what type of gravitational waves do we expect? The two numbers I know off the top of my head roughly are that Jupiter and the Sun orbiting each other radiate roughly 5,000 watts of gravitational radiation, which if you consider the mass of the Sun and Jupiter is almost nothing. Bring it a little closer to home, the amount of energy in the Sun and the Earth is roughly 200 watts. So strap a couple of these light bulbs together, and that's how much gravitational radiation is being released from the Sun-Earth system. And it, you know, you're talking an immense amount of mass, but it's just because the Sun is not terribly dense or highly massive, and the Earth is far away, a number of factors like that. But technically, yes, the Earth is slowly moving in towards the Sun as it radiates gravitational energy. I don't remember the stat off the top of my head, but again, it's one of those measured in proton radii per decade type of statistics, yeah. Other questions? I'll be happy to answer any after informally as well, but any other while we're on the mic?
What is the objectives that say the naysayers have? So when people say they disagree,
Sure.
I'm sure they have some.
So what are the objections to the model? And the idea is gravitational waves, as we discussed, are stretching and shrinking space. So if you have particles on that space, if we had, say, a sheet on here or a trampoline, any sort of thing like that, and you pull the center of it up, you can make those objects move closer together, but it's really just the space between them shrinking. So it's a bad analogy here on Earth, but their idea is that the space between objects is shrinking and stretching, but the objects themselves don't feel the acceleration. They're not actually moving, you're just kind of moving the space in between them. Otherwise, for example, the universe is expanding. The charges in a galaxy very far away should be emitting a crazy amount of radiation if that were the case. So that's one of the primary arguments, is that it's just the space. But the thing is, when we go ahead and look at, say, a charged gas cloud, which we have lots of in astronomy, even if the charges aren't feeling that acceleration, we see A, it produces the same electromagnetic signature as if it were radiating, and B, most importantly, tying back to my earlier research, is that you've now destabilized that cloud. So you've started that cloud moving. So even if you say, hey, it's just the space changing, then I can say, well, now these two charges are closer together. And you have to agree to that if you're going to say that the space is shrinking. If you've changed the separation of those charges, you've changed all the electrostatic forces. Now they want to repel, they want to move, they want to accelerate. They accelerate, they're radiating. So even if it's not necessarily the true motion of the gravitational wave that is accelerating them and causing them to radiate, the fact that you're moving them closer together and now they want to push apart, that's accelerating them, which should also cause them to radiate. That's an excellent question, though. All right.
I'm having a little bit of a hard time getting my head completely wrapped around this. This is really interesting.
Sure, sure.
But it's just sort of like what you're saying with the space contracting around it and whether the particles themselves will feel it. Is that sort of like where you don't feel time dilation if you're traveling very quickly, but yet if we had a powerful enough telescope to see, say you going by that hypothetical rocket ship, like I could see your clock move slower. Or
Kind of. The analogy that I'll use that I can think of best is, say we have a very, very large trampoline and we put something really heavy at the middle. If you and I are standing on either side, we feel some amount of curvature. And if you shrink the distance between us and you shrink everything equally, then we still feel the same curvature. So even though you and I are now closer, we still feel the same curvature. It's kind of a poor analogy, but that's probably the best I can do on that one. I'll be happy to talk more at length on that one.
Is this kind of using quantum mechanics?
This specifically doesn't use quantum mechanics. The massive disclaimer that I should have thrown up here is that everything we do is to first order. We ignore a lot of higher order effects. In my earlier presentations, for anyone that's watching on YouTube, there was lots and lots of slides about the limitations and things like that. Since I just wanted to kind of go over it conceptually, I trimmed some of that out since we didn't have a lot of time. But there's a number of limitations, and there's a number of higher order effects which we kind of push to the side for the moment. So this specifically doesn't use quantum mechanics, but in order to do a complete picture, that would be necessary eventually, absolutely. All right, shall we wrap it up? And I'll be happy to answer more questions afterwards. Sound good? All right, thank you very much.
Thank you for coming, everybody. You cannot imagine how happy I am to hear this presentation from Mitch. I would definitely say, without a doubt, this is probably one of the best presentations we've ever had at a research meeting. And if we contributed, Mitch has been a member of the research group for a very long time. And if any of our activities at the research group contributed to him following his quest for PhD, then I'm very happy. I don't know if that's the truth, but at least we had the environment where people could come, like-minded in astronomy and investigate, which is actually something rare, I would say, to NJAA. We definitely have that type of atmosphere here, which you don't see everywhere. So really, I mean, I'm just very happy that Mitch is he's going into a career in astronomy, going for his PhD. And I mean, as you could tell from, I mean, I work with PhDs in my job and research. This is PhD level work. I mean, as Wayne would say, if you know, when you start talking about, some things in astronomy, it's like, if you can't understand the equations, don't even think about it. I mean, those were not easy equations either. But this is definitely a PhD level work, PhD level research, and I think it was very well done, and you fielded some tough questions too. So, but thank you very much. I'll give you another round of applause there. And again, thank you everybody who came tonight.